In our last lesson, we used the trigonometric ratios to solve and calculate the lengths of various sides of our right angle triangle. In this lesson, we'll focus on calculating the angles in these various right angle triangles. In order to do this, however, we need to know a little bit about our calculator, specifically a second mode that allows us to look at what's called the inverse ratios. So for every sine, cosine, and tan trigonometric ratio, there is an inverse one that we're going to need to be able to use to solve for angles. And we can usually find these by going to some sort of mode or second function key on our calculator and pressing that, which will bring up our various inverse sine, cosine, and tan ratios. So, to practice this, let's look at a few examples. So we have this question here, the statement it says, the sine of some angle theta equals 0.667. Now the sine of an angle equals this, but we're interested in what is the value of just the angle by itself. And that is where the inverse ratios come in. So if I bring up my calculator, and I type in 0.667. So the sine of an angle equals 0.667. If I go to my trigonometry section and I press the second button, suddenly all the inverse ratios come up. I'll unclick this. You'll see it says sine, cosine, tan. Use the second button feature here. I get the inverse sine, the inverse cosine, and the inverse tangent. So if I want to know what this angle is, I type in 0.667, and then I use the inverse sine feature, and it gives me the actual angle, which is 41.8 degrees, rounded off. Here we're told that the cosine of some angle equals 0.667. So once again, we'll type in 0.667, go to the trig feature, press my second function button, and then go to the inverse cosine. Press that, I get 48.16, which rounds to 48.2. Clear that. Here we're told that the tan of some angle equals 0.667. And if I type in again 0.667 and then go to the second function, brings up the inverse tan, press that, and it gives me 33.7. Now for this to work, you have to make sure that you are in degrees mode. Okay, every calculator, at least the scientific calculators that we should be using, have a radians, a gradients, and a degree mode. Make sure that your calculator is set to degree mode, or else these features won't work as expected. All right, let's put this to use in a more concrete example. We're told to find the angle shown. Well, our reference angle shown is angle C. So we want to know what angle C is. We're told that one of the sides is 11 centimeters and another side is 6 centimeters. Since C is our reference angle, we can know that this is going to be our opposite and this is going to be a hypotenuse. Now, a good idea when you're doing this, especially when you're just starting out, is to always label the sides of your triangle relative to the reference angle. So relative to this angle, this side is opposite, this is hypotenuse, and this is adjacent. Now, what do we know? We know the hypotenuse, we know the opposite. So we come over to our chart here and ask ourselves, which of these sine ratios deals with opposites and hypotenuse? Well, it happens to be the sine ratio. So we can say that the sine of some angle equals opposite over hypotenuse. Or more specifically, in this case, we can say that the sine of C equals 6 over 11. 6 over 11 can be written as a decimal. We want to get this in decimal form because we'll be punching these numbers into a calculator, and this is just easier to reference. So we can make a statement that says the sine of angle C equals 0.5454. The sine of angle C equals this. If we want to know what C is by itself, we need to write a statement like this. C by itself equals the inverse sine of 0.5454. This is how we isolate C on this side. We write C, and to get rid of this and bring this over here, we write what's known as the inverse of whatever this is. And if we punch this into our calculator, I'll put in 0.5454, go up to my second and get the inverse sine, and it gives me an angle of 33.05, which will round to 33.1. Therefore, angle C is 33.1 degrees. In this example, we're asked to find angle T. So angle T becomes our reference angle. Always start by labeling our sides. So relative to our reference angle, this is the opposite, this is the hypotenuse, and this is the adjacent. What do we know? What are we told? Well, we're given the adjacent and we're given the opposite. Looking at our chart over here, if you're given the opposite and the adjacent, this tells us that we should use the tan ratio to set up our equation. So we can say that the tan of angle T equals 4.5, the opposite, over 6.5, the adjacent. 4.5 over 6.5 as a decimal becomes 6923, so we can say that the tan of angle T equals 0.6923. If the tan of T equals this, and we want to know T by itself, we can say that T by itself equals the inverse tan of 0.6923, which gives us a value of 34.7. So we can say that angle T is 34.7 degrees. In this example, we're asked to find angle M. So angle M becomes our reference angle. Relative to our reference angle, we know that the adjacent is 2 centimeters. The hypotenuse is 3 centimeters. We don't know what the opposite is. So if we know these two sides, we need to come over to our chart and find a ratio that uses adjacent and hypotenuse. And it just so happens that the cosine uses adjacent and hypotenuse, so we'll use the cosine ratio to carry on from here. So we can say the cosine of this angle, M, equals 2 over 3. Adjacent over hypotenuse is adjacent 2 over hypotenuse 3. The cosine of M equals 2 over 3. 2 over 3 becomes 0.667. So if we know that the cosine of M equals 0.667, then M by itself is the inverse cosine of 0.667. And our calculator will then tell us that our angle M is 48.2 degrees. Here, we're asked to find out this angle C from triangle 2. But if you look at triangle 2, you'll see that we only know one side. And knowing one side is not enough information for us to solve for the angle C. However, this side right here, BC, is common to this triangle. They share a side. We have enough information about triangle 1 to figure out what this side is. Once we figure out what this side is for triangle 1, we'll have the length of a side for triangle 2. So we'll start by using the information we have and solve triangle 1 first. So what do we know? We know that triangle 1 has a reference angle of 23 degrees. We want to know what the opposite side is, because that's the side that has the shared side. And we're also told that the hypotenuse is 18 centimeters. This basically restates what we know so far. So, we're interested in a trig ratio that deals with the opposite and the hypotenuse. What ratio deals with opposites and hypotenuse? According to our chart, it's the sine ratios. So we can set up a statement, a sine statement, for opposite over hypotenuse. For triangle 1, the sine of angle 23 equals opposite, we don't know what that is, we'll just call that x for now, over 18. We'll solve for x, and then we'll know the length of this side. So if sine 23 equals x over 18, we'll use standard algebra. Tells us that x equals 18 times sine 23. And with a few presses of the calculator, 18 times sine 23, it becomes 7. So we know that this value, this side right here, has a length of 7. So let's clean things up a bit. We'll just focus now on the triangle 2. From our previous calculations, we've discovered that this side is now 7, this side is 6. We now have enough information to figure out what this angle is right here. Let's set up our equation. So we have adjacent and we have hypotenuse. Looking at our chart over here, we can see that when we have adjacent and hypotenuse, we should use a cosine ratio to solve our problem. So we'll set up a little cosine equation here. Cosine equals adjacent over hypotenuse. For this triangle, the cosine of C equals 6 over 7. C by itself becomes the inverse cos of 6 over 7. And our calculator then tells us that C has a value of 31. Now in this question, we're told that our reference angle A is right here. We're given three sides. We're given the adjacent side, the hypotenuse side, and the opposite side. We want to know what the angle is. Since we're given all three sides, we could use all three trig ratios to calculate the sine. If we do it correctly, we should get the same value from here, here, and here. Let's work through it and let's see if that's the case. So, the sine of A will be opposite over hypotenuse, which is 4 over 5. A by itself will be the inverse sine of 4 over 5. A is 53.1 degrees. The cosine of this angle asks for the adjacent over the hypotenuse. So the cosine of angle A is 3 adjacent over 4 opposite. A isolated by itself becomes the inverse cosine of 3 over 5. Punch that into our calculator. We come up with a value of 53.1, which is expected and also comforting. We've just confirmed what we already knew from the sine ratio. We've confirmed it using the cosine ratio. And lastly, we have the tan ratio, which asks for the opposite over the adjacent. So the tan of A will equal the opposite 4 over adjacent 3. Tan A equals 4 over 3. A by itself will equal the inverse tan of 4 over 3. Punch that into our calculator. Once again, we come up with a value of 53.1 degrees. So we have triple confirmed using sine, cosine, and tan that this angle A is indeed 53.1 degrees.